Okay, so today we are going to deal with charge distribution. Okay, so what is charge distribution? Right. So charge distribution, see basically when we are dealing with distribution factors, right? So we'll be distributing it in three different cases. Okay. So நம்ம இதுக்கு முன்னாடி வந்து even in your 11th standard you would have studied something called as density. Okay. What is density? Mass by volume. Okay. So ஒரு குறிப்பிட்ட வால்யூம் குள்ள எவ்வளவு மாஸ் நீங்க அடைக்க முடியுதோ that is what is its density. Correct? Yes. So in this case we are going to deal with charge densities. Okay, we are going to deal with charge densities. So how the charge densities are going to be அப்படின்றத first பார்ப்போம். So number one, you are going to call we are going to deal with line charge distribution. So basically line charge distribution is nothing but line charge density or linear charge density. It is basically one dimension. We'll see what it is. Okay, and then surface charge distribution, and it is basically two dimension. And then volume charge distribution. Basically this is three dimension. Okay, so what are these dimensions? Basically one dimension is going to be linear, either x or y or z, right? Likewise two dimensional is going to be a plane, right? xy, yz, zx, and three dimensional is going to be xyz. Okay, so the charges are going to get distributed over these surfaces in different dimensions. Okay, we'll see what it is. So to begin with, we'll deal with line charge distribution. So line charge distribution. Suppose if I take a wire, okay, whose length is going to be undetermined. Okay, so let it be a line charge. I mean line of wire. Okay, so what I'm going to do is I'm going to have charges on it. So what has happened actually? The charges have been distributed over this length. Yes? Okay. So we have something called as densities. We call this as line charge density. Okay. Basically according to mechanics the density was rho is equal to mass by volume. Correct? In this case we are going to deal with charge densities. So line charge densities are mentioned as lambda. Okay. So lambda is equal to, instead of mass you are distributing charges. Okay. So let me take the charge distribution as Q. And it is distributed over the length here. So lambda is equal to Q by L is going to be line charge density. What we call this as line charge density, or even you can write it like linear charge density. Okay, and basically if you take the total charges which is distributed as Q and the total length as L, then this will be happening. Suppose if you take only small amount of charge or a small amount of length, then the line charge densities can be written like lambda is equal to dq by dl. Okay, what will be its unit? Basically charge per unit length is coulomb per meter. Is that clear? Right? So this is nothing but what? Line charge distribution. Is that clear? Right? Yes. And then the next part is surface charge distribution. Right? So if it is surface charge, what you will take? You will take a plane. Okay? So let me take a plane. Say you have like this, right? And you are going to distribute the charges inside the surface. So it is not necessary that it should be always positive. You can also take negative. Okay. So I have distributed Q amount of charge, say for example, through the entire surface. Okay. Now this charge densities are going to be denoted as sigma. Sigma is going to be surface charge density, and if I take the total charge as Q and its area as A or S, whatever you take, then the surface charge density will be Q by A. And if I take one small particular area, say if it is going to be this, okay, and the surface area is going to be ds or dA, and if I want to know what is going to be the surface charge density here, I will take only the charges which is present inside this surface charges. So let me take, surface, let me take it as dq. then the surface charge density will become now sigma is equal to dq by ds or dA. Okay, and what is going to be the unit here? Coulomb per meter square. So this is nothing but 2 dimension. The previous one was 1 dimension because you took only a line. In this case you have taken an area which is going to be a plane, right? So it is going to be distributed over 2 dimensions. Is that clear? Right? Nothing will happen, the same dq by dl only will be there. Why? You have taken only one surface, no? That is not an issue. Okay, right. Charge is coulomb, no? Area is meter square. So coulomb per meter square will be the unit. Okay, right. So next is going to be volume charge distribution. So in this case, if I take a volume, say I take a cube, okay, I am going to have the charges which is filled inside this volume of cube. Right? So if I take the entire volume as V and the amount of charge which is filled is Q, then what will be the charge density here? Let me take it as rho. So rho is going to be equal to Q by V. Okay? Or otherwise, if I take a small particular volume and if I find out what is going to be the charge density, then rho will be equal to dQ by dV. And the unit is going to be coulomb per meter cube. And this is going to be what type of dimension? 3 dimension. Okay? So this is nothing but continuous charge distribution. So the charges are distributed over the surfaces, over the length and over the volume, so that you can find out what is its surface charge densities, line charge densities and also its volume charge density. Okay, right. Say for example, in this case, okay, say for example in this case, I have taken a line charge, correct? Suppose if I take a ring, okay, say this is nothing but the ring, right? So a ring is going to be actually a circular one, right? But it is going to only have the length where I can distribute the charges. Okay, so suppose if I want to know what is going to be the surface charge density for a ring if I have charged the ring. Okay, whose radius is going to be r, right? So charged ring is going to have a density of sigma, lambda is equal to Q by L. What is length of a circle? Length of a circle, it's nothing but 2 pi r. So the charged ring is going to have a charge density of Q by 2 pi r. Is it clear? Right? So this is going to be line charge density. Why am I telling it as line charge when the circle is going to be 2 dimension? See, circle can be 2 dimension, but the charge is distributed over the length of this circle. So it's going to be line charge density. Is that clear? Right? Okay, fine. Okay. Suppose if I have the same case in this, if I take a sphere, okay. So if I take a sphere and I am charging it completely, what will happen to the charges when I deposit on the sphere? It will go and deposit on the surface of the sphere, which is nothing but area of the sphere, right? So in this case, the charge density for sphere which is nothing but given as sigma is equal to Q by S or A. Okay, so it will be what? Q divided by surface area of sphere is 4 pi r square. So this is going to be the surface charge density of the sphere. See this, no? You have a ball. It is going to be in sphere, correct? So if I deposit some charges on this, the sphere surface is going to be completely charged, correct? So if the surface is getting charged, no charge is entering into it. So the volume is vacant, but the area of the sphere is completely charged. That's why it is coming under surface charge density. Is that clear? Right? See, sphere is 3 dimension only, but the charge which is deposited on the surface is only going to be on the surface area, not the volume. Okay, so the charge density of sphere is going to be q by 4 pi r square. Is that clear? Right? Yes. Suppose we will do this some. Okay. In order to make this more interesting, what we are going to do is we are going to find out what is going to be the force and the field when I bring a test charge near this line charge density. Okay, we will find it out. Okay, fine. So we saw the line charge density as you have a line which is going to be having a charge deposited on the length. Correct. What I'm going to do is I'm going to bring a test charge till a distance of say r, right, and the length which I take is, let it be dl, right. Okay, so now the force of attraction or repulsion between these two charges, see, I'm not taking the entire length, I'm only taking this part of length where the amount of charges within this length is only going to contribute for the force. Okay, and we know the force is going to be what? F is equal to k q1 q2 by r square. And again, I am not going to take the total amount of force because I am only getting this particular length. Okay, why am I doing this? See, basically when we have a continuous charge distribution or a very huge quantity of thing, what we do is we take small amount of thing and first evaluate what is coming out of this, and then we will elaborate it by integrating it. Basically what we will do that, right? The same here. So for this small amount of length, the charges are deposited, and for that respective charges, what is going to be the force which is influenced by this charge? That we have to find out, and then we will elaborate it for the entire amount of charge density. Okay, right. So for this I will take df, correct, and then k, and the amount of charge which is going to come is going to be q naught, and q2 is going to be dq because the small amount of charge divided by the total distance between them. Okay, and according to charge density we know lambda is equal to dq by dl, and can I take dq as lambda into dl, and can I substitute it here? If I want to know the total force, what I will do, I will integrate it on both sides, correct. So k q naught dq by r square, it will give you force. So k q naught is going to be constant coming out, instead, and also even r square. So integral, instead of dq what you can do? Lambda dl. So this is going to be the force between the charge and the line charge density. Okay, so if I have a wire which is completely charged and I bring another charge, what is going to be the force influenced by that charge due to this charge density is this. Okay, if you know what is going to be the charge density and what is going to be the length which you take, you can substitute it and you can find out what is going to be the total force. Is that clear? Right? Okay. And also we were discussing that we will talk about field. Okay, so basically what is electric field? Electric field is nothing but force per test charge, right? Whatever charge you bring in, that will be in the ratios to the force, correct? Okay, what is force which we have calculated here? K q naught by r square integral lambda dl whole divided by q naught. So this q naught cancels, k by r square integral lambda k by r square integral lambda dl. So this is going to be the electric field. Yes, clear, right? So this is what is electric field, and this is going to be the force due to continuous charge distribution, or which means line charge density. Is that clear? Do you have any doubts? It depends on the surface la. இப்போ even surface ஆ இருந்தா அதுல ஈக்குவலா டிஸ்ட்ரிபியூட் ஆயிருக்கும். இப்போ நான் ஸ்பியர் எடுத்தேன், அது எல்லாத்துக்குமே ஈக்குவலா டிஸ்ட்ரிபியூட் ஆயிருக்கும். சப்போஸ் ப்ரொஜெக்ஷன்ஸ் இருந்துச்சுன்னா கண்டிப்பா அதுக்கேற்ற மாதிரி அது டிஸ்ட்ரிபியூட் ஆயிருக்கும். இப்போ சொரன்னு இருக்குன்னு வச்சுக்கோங்க, அங்கே பீக்கில் இருக்கும்போது சார்ஜ் அந்த மாதிரி ஒரு மாதிரி இருக்கும், கீழே வரும்போது வேற மாதிரி இருக்கும். It depends on the surface. So next we were discussing on surface charge distribution, right? So for this also, what you can do? You can take an area, right? Say for example you take like this, I have an area which is completely charged. Okay, you have taken a charge, right? So, and then what you do, you take a particular surface area, right? Let this be area ds, and the amount of charge which is present, let it be dq. So, the surface charge density sigma will be equal to dq by ds here. Again, you bring another charge q naught, right? So, to a distance of r, and you find out what is going to be the field, force basically. Okay, so what is going to be the force here? F is equal to k q naught dq by r square. If I integrate it directly now, you know what it is, correct? And also from this I can calculate dq is equal to sigma ds. Can I substitute here? So we'll be having F is equal to k q naught sigma ds by r square, correct? Yes. Okay, so if that is the case, then you will have k q naught by r square integral sigma ds is going to be F. So this is going to be the force experienced due to the surface charge density. What about the field now? Can I write it directly? Yes, what will be? K by r square integral sigma ds. So this is going to be the electric field due to surface charge density. Is that clear? Right? Okay. So likewise, volume charge density. Okay. In this case again the same. So what is going to be the force? K q naught by r square integral. Now, so if you can replace this, dq is equal to rho dv. So substitute it here, rho into dv. So this is going to be the force when you bring a charge near this volume charge density. And what will be the field now? K by r square integral rho dv. Clear now? Simple, right? Clear? Any doubts? And also, since force and electric field is vector, you can also mention it in vectors. Okay, say for example, for line charge density. Okay, again when you are using vectors, what will happen? If you have F vector, then this will be r cap, correct? Likewise, E vector, this will become r cap, right? So likewise, when you do it for here, F vector, r vector, E vector, r cap, right? Likewise, for this, it's going to be again F vector, r cap, E vector, r cap. Is it clear? Right? So this is all about continuous charge distribution. See this question, 2 point charges QA is equal to 3 microcoulomb, QB is equal to minus 3 microcoulomb are located 20 centimeter apart in vacuum. Okay, so what we will do is first we will sketch what is happening. Okay, so let me have QA here and QB here, and QA is going to be plus 3 microcoulomb and QB is going to be minus 3 microcoulomb, and they are going to be separated by a distance of 20 centimeter, right? And then what is given? They are asking us to find what is going to be the electric field at the midpoint O of the line joining AB, right? So the charges are this A and B. Say it is going to be A, this is going to be B, this is going to be the line joining A and B. So let me have this as midpoint O. So if it is going to be midpoint, the distance between these two is going to be 10 centimeter and this is going to be 10 centimeter, correct? Okay, they have asked us to find what is going to be the electric field at this point. Okay, fine. The electric field at this point O is going to be because of both the charges, correct? Okay, let me take first QA. So according to QA, the electric field direction at O will be, we have seen lines of force, right? Yes, so it is positive charge. So obviously it will move away, correct? So the electric field due to A will be towards OB, correct? And in the case of minus 3, it will move towards B, correct? Because negative charge, no, it will move towards the charge, and positive charge, it will move away. So you can see at this point O, both the electric fields are in the same direction. So can I say E is going to be EA plus EB? Because they both are going to be on the same direction. Okay, now what is EA? So electric field due to charge A at O is going to be what? What? 1 by 4 pi epsilon naught Q is going to be 3 into 10 power minus 6 divided by OA square, which is going to be 10 centimeter, no? So 10 centimeter to meters you have to do. So 10 into 10 power minus 2 whole square. Yes or no? Because centimeter you have to convert it into meters. So what you will do? You have to multiply it with 10 power minus 2. Right, okay. So how about EB now? 1 by 4 pi epsilon naught. What is it going to be? 3 into 10 power minus 6 whole divided by again 10 into 10 power minus 2 whole square. I am taking magnitudes alone because anyways the direction is going to be the same. Okay, right? Okay. So what you have to do? You have to add these two. So if I add, what you will get? E is going to be, so if you add these two, 1 by 4 pi epsilon, everything is common. So it's going to become 2 times. Correct? So if it is going to be 2 times, what you will get? So 1 by 4 pi epsilon naught, you can take it like 2 into 9 into 10 power 9, 1 by 4 pi epsilon naught, and into 3 into 10 power minus 6 whole divided by 10 power minus 2, because 10 into 10 power minus 2 is 10 power minus 1, whole square is going to be 10 power minus 2. So what you will get? 18, 18 3s are 24, 2, how much? 54, right? So 54 into 10 power 2 mala poiduma, 10 power 11, so 10 power minus, sorry, plus 5, correct? So 10 power 2 mala poshna 10 power 11, 11 minus 6 is 5. So 54 into 10 power 5 is going to be your electric field, and the unit is going to be NC inverse. Clear? Right? And the direction of electric field will be, obviously you know it is going to be along OB, right? So it is going to be along OB, right? Okay. So this is going to be first part of the question. And what is the next part? If a negative test charge of magnitude 1.5 into 10 power minus 9 coulomb is placed at this point, what this point means? This O. If I place 1.5 into 10 power minus 9 coulombs at this place, what is the force experienced by the test charge? So how much amount of force will be there? Simple. What was electric field which we got? 54 into 10 power 5 NC inverse. Correct. And how much amount of charge is placed here? 1.5 into minus 9 coulombs. Correct. Okay. What is the force they are asking, right? So basically you know E is equal to F by Q. So what will be F? Q into E. So you know Q now, 1.5 into 10 power minus 9 into 54 into 10 power 5. So what will be? So 54, 1.5, 20, 25, 27, 4, 5. So 0, 11, 8. So 81 into 10 power minus 4. Unit is Newton. So this is the amount of force which we have when you bring in the charge at that position N, O.